Hello and welcome. You know, we all take for granted that computers are just incredible at math. But have you ever stopped to wonder how we actually teach them to understand something from algebra class, like a polynomial? It's a really fascinating translation puzzle. So let's get right into it.
So let's take a familiar expression, something like 3x squared plus 5x minus 2. For you and me, that's a straightforward piece of math. But for a computer, that's really just a string of characters. It doesn't see the concepts. So how in the world do we translate that abstract idea into something a machine can actually compute with?
And this right here brings us to what I like to call the polynomial puzzle. The real challenge, you see, isn't the math itself. It's how we organize the information. We need a really structured, predictable way to store the essential parts of a polynomial, every single coefficient and every exponent, so the computer knows exactly what it's looking at. Okay, so first, just a super quick refresher. A polynomial is just an expression made of variables, like x, raised to whole number powers, and coefficients, which are just the numbers out front. Then you just add or subtract the terms. Pretty simple stuff. So what's the secret? How do we crack this puzzle? Well, the solution is surprisingly elegant, really powerful, and it's a fundamental tool in programming: the array. It is the perfect data structure for this job. And this brings us to the big aha moment. This is the core idea where the abstract world of math slams right into the concrete, organized world of code. The whole logic boils down to just two simple rules. First, the position of an item in the array, what we call its index, that's going to represent the exponent. So index 0 is for exponent 0, index 1 is for exponent 1, and on and on. Then, rule 2. The number we actually store in that position, the value, well, that's the coefficient. And that's it. The index is the exponent, the value is the coefficient. That's the whole game. All right, let's make this crystal clear. We're going to see this principle in action with a real example. Let's map a polynomial, piece by piece, directly into its array form. Here is our polynomial: 5x to the fourth plus 3x squared plus 7x plus 1. Now pay attention here. Notice it's missing an x cubed term. That's actually pretty important, as you'll see. So let's break this thing down. When we break it down, you can see how cleanly each piece gets separated. The term 5x to the fourth, that's an exponent of 4 and a coefficient of 5. For 3x squared, the exponent is 2, coefficient is 3. For a 7x, well, that's really x to the power of 1, so exponent 1, coefficient 7. And the constant, 1, that's technically 1 times x to the power of 0. So exponent 0, coefficient 1. Now, if we just follow our two simple rules, this whole breakdown translates directly into one single, clean array. And here it is. It's beautiful, isn't it? At index 4, for the exponent 4, we store the value 5. At index 2, we store 3. But now, look at index 3. Remember how our polynomial had no x cubes term? We simply put a 0. That 0 acts as a placeholder, and believe me, it is absolutely essential. And this brings up a really important question. What do we do about these missing terms? What happens when a polynomial is sparse, meaning it has a lot of gaps? Well, that 0 we just saw, that's the whole answer. So the most crucial point here is that 0 acts as a placeholder. It holds the spot. For a polynomial like 4x cubed plus 2x, the coefficient for the x cubed term, which is 4, goes into index 3. The coefficient for the x term, 2, goes into index 1. And since there's no constant term and no x squared term, we just plug zeros into index 0 and index 2. This keeps the whole structure perfectly consistent. Okay, so now that we know how to store a polynomial, let's actually do something with it. A really classic exercise in a lot of computer science courses is adding two polynomials together. And with our array method, this becomes incredibly easy. Let's see how. So we're going to add two polynomials. We'll call them A and B. Polynomial A is 3x squared plus 2x plus 5. And polynomial B is 4x cubed plus x squared plus 3. First things first, we convert both of them into their array forms. We make sure they're the same length just by adding zeros if we need to. So array A becomes 5230, and array B becomes 3014. When we line them up by index like this, it's basically the computer's way of lining up all the like terms. And now for the magic. To add the polynomials, we just add the numbers at each matching index. That's all it is. It's called an element-wise addition. So at index 0, we add the constants. 5 plus 3 gives us 8, and we just keep going right down the line. At index 1, it's 2 plus 0, which is 2. At index 2, we've got 3 plus 1, which is 4, and at index 3, it's 0 plus 4, which is 4. And just like that, boom, we have our result array. Now, we just take that result array, 8244, and translate it back into math. The value 4 at index 3, that's our 4x cubed. The 4 at index 2, that's 4x squared. The 2 at index 1 is our 2x, and that 8 at index 0, that's our constant. It's simple, it's clean, and for a computer, it's incredibly fast. And this isn't just some theoretical exercise. As this quote shows, this exact problem, adding sparse polynomials with arrays, is a classic foundational lab you'll find in computer science programs all over the world. It's designed to teach this core concept of data abstraction.
So why do we even learn this? Why is this method so important? What's the big picture here?
Well, there are 4 really big reasons. First, it's simple. The logic is so straightforward to write in code. Second, it's efficient. Adding and subtracting is super fast. You're just looping through arrays. Third, it is the perfect example of data abstraction, taking a math idea and turning it into a structure a computer can use. And finally, predictability. The memory size is fixed. You know exactly how much space it'll take up from the start.
But no solution is perfect for every single situation. This array method has a key limitation, and understanding that is what pushes us to the next level of thinking in computer science.
So this method is elegant, for sure. But what happens with a really, really sparse polynomial? Like, say, x to the power of 1,000 plus 2. To represent that, you'd need an array with over 1,000 slots, and 999 of them would just be filled with zeros. Is that really an efficient use of memory? That question right there is what opens the door to other, even more powerful data structures, like linked lists. But that's a topic for another explainer.